Thank you for the introduction, and thanks to the organizer for inviting me. I'm Kelly LUO. I'm an assistant professor at University of Southern California. So I changed my talk a little bit. I'll talk about our two main work recently on the direction of spin torque in magnetic heterostructures. And one is particular spin filtering detection of interferometry resonance. The paper is coming online tonight. And then the other one is ultra-fast Sagnac current interferometer. So without too much introduction to the expert in this audience, what we're working on is very much overlap with a lot of your interests. Is we're working this zoom of 2D Van der Waals materials, and as you know, 2024, the first graphene was realized, and then in 2010, the first optical 2D material, transition metal dichalcogenide, was demonstrated. And for a while, what about spin? And magnetism hasn't been realized in 2D material for a while, but till recently, in 2017, and the audience see that some of the was done by the pioneers in the audience as well. The first 2D magnet was realized. So our work, or our group, largely working in these interdisciplinary large area of 2D magnetic heterostructures for different kind of interface and phenomenon and technology. So we have done works in charge spin conversion, optical spintronics, and magnetic tunnel junction, which I'll talk more today. And also there's as well as spin orbit torque. As some of your experts know that this field has really a vibrant emerging opportunities and excitement in all different directions, including twists, which I won't touch too much today. So we are a relatively young group. We're our group, Ultra-Fast Quantum Optical Spintronics Group at University of Southern California. It's barely about 2 years old. We started about late 2023. Our lab is mostly built up now. We have about, in the lab is over 2 scanning optical microscope with superconducting vector magnet. One is the AlloCube, the other one is CryoMag. We're working on a combination of different ultra-fast and continuous wave lasers, ranging from mid-IR ultra-fast, and this is one is being built, and also as well as Sagnac interferometer, which I'll talk more today. And we also characterize and making our device in-house through these automatic glove box, and student working in the clean rooms to make those samples. We're recruiting, so if you know of anyone who's interested in looking for a postdoc or either joining a grad school or even coming here as a visiting scholar, please refer them to us, and we're happy to talk to them. We're also actively working on different kind of facility. I was just coming back from BESI last night. So we worked on the Nexus facility at Ohio State, which look at or trying to develop time-resolved RPETs as one of the things that in the US is this mid-scale facility trying to develop. And we come to BESI too often to look at time-resolved Stickson scanning transmission X-ray microscope to try to look at those magnetic dynamics. And we're also actively working with Lawrence Berkeley National Lab looking at the spin polarized link, or as the first speaker talked about link, and we're looking at the surface polarization of those, a lot of those 2D materials in using spin polarized version of the link. Right. So one of the motivation for our field is try to look at how to manipulate materials, magnetic material using electron spin. So in the, let me use a mouse. In the industry, people has been using, oops, the mouse. In the industry, people has been using this thing called spin transfer torque, which is a basic concept of a magneto-tunneling junction where you have 2 layers of ferromagnetic. One is a free layer, the other one is a fixed layer. Where the fixed layer, where you're passing a electron vertically through the structure, and the electron will be polarized by the fixed layer. And once exiting the fixed layer, going through this decoupling tunneling barrier into the free layer, the spin momentum of the electron will passing its momentum onto the free layer, and thus exerting this angular momentum transfer. And this is a concept of spin torque. And the spin torque is acting as a reading and mostly as a writing mechanism for the free layer, which is your memory layer. And so this spin transfer torque has been in major silicon foundries since before COVID, 2018, 2019. But we look at the structure, there is one fundamental limit of this energy limit, in the sense that every electron can only carry its maximum momentum h bar over 2 and transfer its momentum into the fixed free layer and then exiting the system. So by that, there is a fundamental limit in the energy efficiency in this way. So spin orbit torque is a parallel concept that overcome this fundamental energy limit. Instead of using a tri-layer spin orbital, using a bilayer, where you use a spin source or something with a large charge to spin conversion, and right next to it, putting a layer of magnet. And in this way, the electron flowing into the spin source can be polarized many, many times, and then transferring the spin momentum onto the magnet before exiting the structure. So this overcomes the fundamental limit of h bar over 2, and theoretically should have much higher energy efficiency. This field has been booming in the past decade or so. The spin source is typically a material with large spin orbit coupling. It can come from spin momentum locks in the topological materials, and it can also come from the bulk spin Hall effect. Right. So our research is focusing, a lot of the research focusing on using spin orbiter to manipulate different kinds of magnetic materials, and in particular 2D material, especially 2D magnets. Both can be served as these magnets layer where you have low net magnetic moments and potentially faster read and write state, as well as good anisotropy down to molar layers. So the outline of today's talk, I want to talk about two work. One is our recent work in the electrical detection of interferometry resonance with electrical tunability damping, and the other one is developing high sensitivity optical spin torque metrology, which is developing Sagnac current interferometer to sensitively detect these kind of spin torque actions. So first I'll talk about the first part. In particular, the first part is motivated by using antiferromagnetic spintronics. So there's a couple of overarching sort of attractiveness of antiferromagnet versus ferromagnets. Antiferromagnet has zero net magnetic moments. It's stable to perturbation from the external magnetic field. And it also has exchange couple between the sublattices, which is richer physics compared to ferromagnet, which give you different kind of resonance mode and mode coupling. And this also has faster dynamics over a wide range because of the stronger exchange coupling. And then now antiferromagnet, many of them also discovered to be an ultramagnet. It's a very exciting field as well. So in order to achieve the spin orbit control of the interferomagnetic resonance, in this particular work, we demonstrate two sort of like beginning steps. The first step is to achieve electrical detection of these interferometry resonance using a spin filtering tunneling resistance. The second step is achieve spin orbit manipulation of the interferometry resonance. Right. So how do we do this? First, we started with chrome-sulfur bromide, which is a van der Waals interferomagnetic semiconductors. And a lot of you have worked on this material. It's a very model system where it essentially has very clean triaxial anisotropy along the A and B and C axis. It's intralayer ferromagnetic order and interlayer antiferromagnetic order. So early on, we have showed that in a bulk chrome-sulfur bromide, we can use a microwave transmission to measure the resonance mode. We can measure the clean out of phase mode and in phase mode. That basically using two lattice LLG. Essentially, we're looking at two ferromagnetic materials interlayer coupled together, so interlayer exchange bias. Right. So is it possible that we can detect this mode down to the atomic thin layer and then making into a more practical device? And this is one of our motivation to go a step further to try to establish demonstrate the device perspective of this material. So from here, we take inspiration from the standard spin torque ferromagnetic resonance, where you can put a magnet on top of a non-magnet. And if you are passing a current through the system, the non-magnet will generate a Ørsted field. And this Ørsted field, if it's a gigahertz frequency, will couple to the intrinsic resonance of the ferromagnetic material. And this kind of resonance is governed by the Kittel formalism, where the omega is the intrinsic resonance of the ferromagnetic materials and coupled to external magnetic field, and as well as the effective anisotropy system coupled to with the damping term. So in this system, in the spin torque FMR, or in short STFMR, one can also read out the magnetic resonance state by using a rectifying voltage readout, where if you drive the system with a gigahertz current and the magnet is response to your driving current, which you have an anisotropic magnetoresistance, if you have two of these sign function time each other, you end up with a DC rectifying voltage. And this is demonstrated in different kind of ferromagnetic system where if you drive the system when they follow the Kittel formula with a particular frequency and the particular magnetic field, you will see a mixing DC voltage when it's on resonance and when the system driving to the resonance mode. And from the line winds of the resonance, one can extracting out the intrinsic damping of the system. Right. So we take inspiration from this work and also a previous work led by some of the people in the audience and using a magneto-tunneling junction to read out the magnetoresistance of a 2D magnet. So we constructed this MTJ geometry using a graphite as the top electrodes and 2-layer crossover bromide and platinum ditelluride as the bottom electrode. Platinum ditelluride is a material with a strong spin-over coupling, and it's also a conductor, so we can use both as a readout mechanism and a writing mechanism. Right. So using this kind of MTJ, we can read out the spin tunneling magnetoresistance in its DC form by applying magnetic field either along the neo axis or perpendicular to the neo axis. One of the along the neo axis will give a spin flip interaction, which you can see this sharper jump. And if you apply perpendicular to a neo axis, you will see this spin flop configurations. So here we demonstrate a DC readout of the magnetization state. The next step is that we putting this device into the RF region, which is basically mimic the spin torque excitation of the magnetic resonance. Again, similar concept as in the ferromagnetic mode, we can read out the tunneling voltage as a rectifying DC voltage as a mixing of the RF current exciting into the channel, as well as a spin filtering magnetoresistance that directly read out the magnetization state of crossover bromide. So by doing this, I think for the first time we were able to read out these 2 layers of crossover bromide magnetic resonance state, and we can see that this kind of behavior that when we sweep the magnetic field, when they follow the condition of resonance, we can see a change in the rectifying voltage. And we can also plot this data as a spectrum, and we verified that this spectrum is similar in the bilayer region compared to our bulk region with a small change in the exchange coupling, which is understandable when you reduce the materials to a bilayer. Right. So here we have first demonstrated that we can have electrical detection of the outer plane antiferromagnetic mode in bilayer crossover bromide. And the second step is moving on to look at how we can manipulate these antiferromagnetic resonance through spin orbit torque. So again, using the same geometry, now we pass the current through the spin source layer. Now the spin source layer not only generating an Ørsted field that gives the resonance, and also injecting the spin into the system. And in this case, we use a platinum ditelluride. And one can then measure the damping of the magnetic layer, and the damping delta is correlated to first the intrinsic Gilbert damping of the system, as well as the spin that's pumping into the system itself. And one can think about if the spin pumping to the magnet, you can work together with the magnet, or you can work against its own damping. And depending on the direction of spin, you can see an enhancement or a decrease of the damping, depending on how much energy is transferring from the spin source layer into the magnet. Right. So previously in a ferromagnetic model, one can measure the line width as a function of DC current applying in the system, and seeing the line width being modulated as a linear fashion, and depending on whether the magnetic field and the current is aligned one way or the other way, essentially the damping is changing proportionally to the sign of the m dot sigma. Sigma is the spin exciting into the system. And so, applying the same concept, we perform the same kind of measurement. And now, in addition to the RF excitation, we also add on to a DC current source, and the DC current generates the spin current through the platinum ditelluride into the crossover bromide. And we follow up the similar kind of ideas, but here, one thing to notice that we twisted our sample 45 degree relative to the crossover bromide is 45 degree relative to the spin source, so that we can have applying the external magnetic field so that we can canted the 2 different sublattices in different configuration. What we found out is that if we apply the magnetic field, let's say H minus, applying to the top right directions, where our line one of the sublattice is relatively spin, the spin is perpendicular to the current direction, we see a change in the overall line width. But if applying the magnetic field along the opposite direction, which will align the other sublattices along the spin direction, we don't see much change in the line width modulation. So this is different than what one observed from the ferromagnetic materials. And this prompts us to find another major main conclusion of this work is that we've shown that in this case of a 2-layer crossover bromide, the line width modulation is selective in the sense that when we apply only when one of the sublattices is aligned to the spin, we experience excitation from the spin torque. And when the other sublattice is aligned from the spin, there's no obvious excitation of the spin torque. Right? This is also suggesting that the spin torque is only acting on the interfacial sublattice layer. And one of the implications of that we're thinking that this shows that for one of the first work that showed that spin torque can selectively excite on one of the sublattices of the interferometry materials compared to the others. And we can also characterize the torque efficiency of the system, which is about 0.29, and is comparable to spin torque on the ferromagnetic materials. And usually for torque efficiency in antiferromagnets, they're relatively smaller compared to ferromagnet because the two sublattices will cancel the torque excitation. But in this case, we've shown that the electrical detection of this antiferromagnetic resonance in this bilayer crisscross-Bowman structure, we can have the spin torque primarily acting on the interfacial sublattice layer. And we can also achieve a comparable spin torque efficiency on the antiferromagnetic compared to a ferromagnet. And this sort of highlights this future opportunity to really investigate the antiferromagnetic resonance in 2D structures, which is at this infancy compared to the 3D world. And also, we're working towards nanoscale gigahertz and terahertz antiferromagnetic resonance that build on these bilayer structures. Yeah. So with that, I wanted to change gear to talk about another direction that our lab is developing, which is developing this high sensitivity optical spin torque metrology using Sagnac current interferometer. So one of our motivations for developing this high sensitivity apparatus is because 2D magnets, such as much smaller magnetic moments, and thus it's more challenging for experimental readout both in transport and in optics. So what we have done in the past few years is constructing these Sagnac optical interferometer and really achieving at least 50 to 100 times better signal to noise compared to the conventional DC mode interferometer. So what I'm showing here is a Sagnac current interferometer readout on this is a platinum cobalt devices, and this measurement taking about 10 minutes, and this is compared to a conventional polar mode setup, and you can see the noise is very, very good, and you can barely see the noise, and this data is taking about 10 minutes. Okay. And this is a diagram of our setup and a picture of setup. Everything is relatively compact. It's a combination of free space and fiber space optics. And this one is set up in the room temperature, and now we can also expand it to the low temperature and high field region. So the next step, I will quickly walk through how this interferometer work. So the Sagnac interferometer, if this is a picture taken from from Wikipedia, was invented about 100 years ago. When at the time that people were looking for ether, so Sagnac interferometer and microsync interferometer was two major apparatus for that. But in the sense that it forms it comes with a light source, and then using a beam splitter to separate the beam into two paths. Therefore, you have two beams. One goes clockwise, the other one goes counterclockwise, but following the same optical path. And if you were rotating this entire apparatus, and if there were ether in the system, then you will see that on the detector, you will see interference because the pathness difference is different for these two beams. Right. So we adopt the same concept. Actually, this was first pioneered by Capuccini's groups in Stanford, where they use this fiber-based Sagnac interferometer to detect pairing P-wave superconductors. And then, so the setup works in such a way that we start with two spatially overlapped but orthogonally polarized beams traveling through the single mode polarization maintaining fiber. And if a cross section of the fiber look kind of like this, so you have a slow axis and fast axis. Essentially, we're launching two beams into this fiber, and these are basically the two beams of Sagnac loop, except that we squash them and have a zero loop area. Right. So then we have those two beams going through the fiber EOM and the phase modulator. And the fiber EOM modulate the phase modulation of the slow axis and fast axis at a certain high frequency. We modulate about 5 megahertz. And once those two beams exiting from the fiber, it goes through the quarter wave plate, which is inside the cryostat, and then reflected back from the sample, and then goes through the quarter wave plate again. So a beam going through the quarter wave plate twice, meaning that this quarter wave plate acts as a halfway plate. Therefore, the beam that going forward in the fast axis will come back in the slow axis, and then go forward in the slow axis will come back in the fast axis. Therefore, we form a Sagnac interferometer loops where the two beams, one beam goes forward fast and come back slow, the other beam goes forward slow, come back fast. And doing that, both of the beings experience the same path length, but they have different phase modulation. And therefore, we sort of constructing the same kind of Sagnac loop in this way. Right. And once we tune the modulation frequency of the EOM, such that we match that omega is a modulation frequency that matches the tau. Tau is a time of flight from the 30-meter fiber loop. You can essentially think about that we're modulating those two lights to constructive or destructive interference at the detector. And then we can calculate the sample. From this, we can basically find out the difference between those two beams in terms of sample curve rotation that when they reflect from the sample. Right. And this can be constructed or detected as a first and second harmonic interference signal at the detector. And once you work out the math by essentially just constructive interference, you've seen that the first harmonic is proportional to the curve rotation and also divided by the curve ellipticity. Curve ellipticity is related to the sample reflection coefficient of the left and right hand circular polarized light. And then similarly, we can also detect from the second harmonic and also has a very similar mathematical form, especially that both of them have an inverse relationship with the curve ellipticity. So we detect both intensity signal, and we have the one divided by the other, and then in this way we can nicely get rid of the curve ellipticity, and we only left with a curve rotation. So this is one of the reasons that the interferometer has much higher signal to noise, because we completely get rid of the intensity fluctuation that come from the curve ellipticity, and we only look at the curve rotation. So once we construct this interferometer, we have this high sensitivity autoplane magnetization. We also look into what is our sensitivity to the in-plane magnetization. And we have done this measurement simultaneously with this is, I think, Platt and Cobo device, and we were able to apply the magnetic field in plane, constant magnetic in plane, and then rotating the azimuthal angle in plane. In the voltage readout, one will read out this sign 2-phi dependence, which is coupled to the harmonical, coupled to the planar Hall contribution that coupled to the in-plane moments. But in the optical readout, we don't see this sign 2-phi dependence within our noise region. So we're actually seeing that this shows that we actually don't have any sensitivity to the in-plane moment within our noise region. We also derive why this is the case. It's in the essay of the paper. And so we essentially only have a readout of the outer plane magnetization, but not the in-plane magnetization. So because of this, we can then, next step, try to develop the conceptual framework, how we can use this technique to detect spin torque excitation. So first, we can use Sagnac interferometer to measure the spin torque by building on the LLGS equation, where it's basically describe the magnetic equilibrium modes when you have a system under the external magnetic field and also a spin injection into the system. Right. So for sample with perpendicular magnetic anisotropy, then the curve rotation, which is proportional to the outer plane magnetization, can be write out as sensitive to the external applied field in the in-plane applied field, and the second order in the small angle tilting from the outer plane direction. And then for example, for the in-plane magnetic anisotropy, the outer plane magnetization, which is directly coupled to the curve rotation, is directly coupled to the first order in the outer plane tilting angle. So there's a lot of jargon on this slide, but essentially that we can read out. Let me go to the next slide. When you have an outer plane magnet, we can read out when you apply an in-plane field, they will have this so-called parabola tilting, where you start the outer plane and start tilting slightly in plane. And you can see that the sensitivity of the outer plane direction is second order onto the in-plane field that's applying. And in addition to that, we can also look at something we call delta theta k, which is basically the current-induced curve rotation, and essentially taking the first derivative of the theta k and looking at this current-induced effect. We can look at the tilting from the current-induced magnetization moment, and the slope here basically measures the spin torque efficiency that's essentially coupled to the current drive. Right? So by measuring these slopes, one can quantify the spin torque efficiency, essentially how much spin is pumping into the magnet. Similarly, we can also measure the sample with an in-plane magnetization, in-plane magnetic anisotropy, where the outer plane, where the theta k, the optical signal, is directly coupled to the outer plane damping torque, which is the in-plane spin generated into system, and try to torque the material outer plane. And this have the symmetry of the cosine phi. Phi is azimuthal angle, and in a measurement we can show that the current-induced curve rotation is coupled to the in-plane magnetic field, which is actually over here, And from fitting the size of the cosine phi dependence, we can figure out what is the damping like torque, which is basically the current-driven effective field in the system. So in this work, we show that this is one of the first techniques that we can both quantify the torque efficiency for sample with autoplane and also in-plane spin, autoplane anisotropy and in-plane anisotropy. In this particular case, we grow a series of a Cobo wedge, which is a Cobo film with different thickness, and by controlling the competition between interface perpendicular anisotropy and then the overall bulk in-plane shape anisotropy, we can obtain a series of a sample with different either autoplane in-plane anisotropy, and we can quantify the torque efficiency to show that roughly speaking they're about 0.1, and they're not completely consistent with each other, but they're not too far from each other as well. And also show that this is often not the case for electrical-based measurement because, as I showed field sites earlier, when you do electrical Hall readout, there are also both an autoplane anomalous Hall effect as well as planar Hall effect. So arguably, optic is actually a cleaner measurement because we're only sensitive to the autoplane magnetization here. So moving forward, we also apply this current interferometer for different kinds of magnets. We've demonstrated the one we demonstrated is on the platinum cobalt, which is a conducting magnet. Sorry, and we can see the Sagnac sensitivity, essentially how big the jump it is, or how many Kerr signal in terms of million radian. And when you move on to the insulating magnet, because insulating magnet don't strongly couple to couple to the light itself, they don't reflect that well, then you will have a much weaker Sagnac sensitivity at a much lower value. But regardless, we will still be able to, because of the sensitivity of our system, this is on a Bismuth YIG, which is an insulator, we can have much smaller Sagnac sensitivity, which is about 40 times smaller compared to a metal system, but we still have the sensitivity to be able to perform these kind of spin torque-driven tilting effects. Yeah. So moving forward, we also apply this to the 2D magnet systems. One of our motivation here is to integrate 2D magnet into the spin torque devices, and particularly this is attractive for ultra-low current switching due to the reduced net magnetization, especially when you have insulating magnets that has the transport readout has been challenging. Optical readout is a very direct measurement for that. So there's some preliminary data that we show that we're working on different kind of FGTs, and we'll also be able to look at, this is a static measurement of a FGT flake, and also looking at current-driven effects, likely due to spin torque effect. So stay tuned. Right. So with that, I want to sort of wrap up my talk. So we're looking really at the different directions in these multifunctional Van der Waals structure for the spin place quantum processings. We're looking at, some of our group is working at looking at spin torque based on ultramagnetic topological material and hoping for like next generation magnetic random access memories. We're also looking at different kind of dynamical measurements that wouldn't have time to talk about it. Hopefully next time. We're looking at dynamics measurement using both our in-house Sagnac current interferometer and also time-resolved XMCD and time-resolved RPETs. And all of this, we're also exploring into this superconducting spin torque region, hoping to really using optical probe as a direct readout of the spin dynamics when you're integrating a superconductor with a magnet systems, and hoping that will provide the dissipationist cryogenic memory for the next generation. And all of that, we work closely with our collaborators on different kind of ball crystal and exfoliate crystal. And so these are the teams I work with. A lot of the work was done in collaboration at Cornell and both at USC. And these are the, this was my postdoc advisors and my grad advisors, and also the collaborator. Now we're working on a lot of those works. So with that, thank you for your attention.